Hello, and welcome to this lecture on the exam exercise from last spring. I have here the exam exercise as it looks, and you can see that it consists of 4 problems, and I'm going to go through it on the blackboard, so to speak. There's also Maple version of this of the solution, a suggested solution to these exam exercise on the homepage. so you can look for it there. But now I think it would be okay to give it on the blackboard. So let me start on the first problem. You have a real function, and say if you want to send messages to me, you can use the chat and ask questions, and I'll try to answer the questions as we get along. And if the sound is not good, or if the quality of the video is not good, then please tell me. But the first problem, we have a function. See here, it's y divided by the exponential function of x. And you know the exponential function of x is never 0, so that's okay. So it's in fact valid all over the R2 plane. And the first question is, we should determine the level curves corresponding to the levels 0 and 1. So let me try to write this on the blackboard. So we start by problem 1. And we're given this function f of x comma y equal to y divided by the exponential function. And I can also write this as y times e to minus x. This is convenient when you have to differentiate this function. So in question 1, we are asked for the level curves corresponding to 0 and 1. So corresponding to 0, you have that y divided by ex, this is the functional value, should be equal to 0. Now, the denominator here is always different from 0. You can multiply on both sides with this, and you get that this is equivalent to y equal to 0. You know that x is a real variable. So this is the x-axis. Now, if I continue here, I get, I should have the level curve corresponding to 1. I have y divided by ex equal to 1. And again, you can multiply with the exponential function. So you get that y is equal to ex. And again, x is just a real variable. So this is the exponential function. So this was in fact the first exercise. Let's have a look at the second exercise. I just go to this, and you see here in the second exercise, you have to determine the directional derivative of f in this point O, 1, and it should be in the direction towards the point 1, 2, and then further on you have to find the largest value that the directional derivative can obtain or attain in this point 0, 1. Let's try to do this. I write here, this is question 2. And we will first need the directional derivative. If we call the point 0, 1 equal to A, we call it A, then we are looking for the directional derivative. And this directional derivative has this form here. So it is the directional derivative in the point A, and then in the direction of this unit vector, and it's given by the formula E times the gradient of F in the point A. So in order to determine this, we need to determine this, this unit vector, and we need to determine the gradient of F. So let's start by determining the gradient of F. And to do so, we need to differentiate just first, for the first coordinate in the gradient, with respect to x. And if we look at this, then y is a constant when we differentiate with respect to x. And when you differentiate the exponential function, you get the exponential function itself. And then you get -1 because it is a composite function. So the result is that you get -y divided by the exponential function for the first coordinate. And for the second coordinate, you just get 1 divided by the exponential function. That is 1 divided by ex. And if you do it in this point here, you could get, I should state that this is a vector, the gradient of f in the point A, and this is equal, now e of 0 is 1, and y is 1, so you get -1, 1. So this is the gradient. Now we're going to get our unit vector, and I just make a small sketch here. So this is 1, this is 1. So we are at this point here. This is point A, and we're looking at the direction towards the point 1, 2. So A is 0, 1, and this is 1, 2. So if we call this vector for V, then we get that V is equal to the final point, 1, 2, minus the initial point, which is 0, 1. So this is the result of 1, 1. But you need a unit vector in that direction. You get that just by dividing with the length of V. So this will be, you see, the length of V is the square root of 1 plus 1, so that is square root 2. And if you divide this by square root of 2, you get square root of 2 half, square root of 2 half. Now you have both the unit vector and you have the gradient in the point, so you can actually write down this directional derivative. This is, I should say it is a derivative. So you need to have this derivative mark. So A, and then you have that it is square root of 2 halves, square root of 2 halves times, and then -1, 1. So it'll be minus this value, plus this value, so it's 0. Let's look at the figure, because you see the gradient here is -, 1. So if I print if I draw this in red, then I have here, the gradient of f in A. So you see, it is perpendicular to that vector here, and this is why the dot product is 0. Now let's return to white. What I'm going to do now is that I'm going to show you well, the last question here, and this is what is the maximum value of this directional derivative. And here I use the general formula for the dot product. So this is equal to the length of E times the length of the gradient times cosine to the angle between the two. And since this is 1, it's a unit vector, and this one here, that is the length of the gradient at the point A. So this is square root 2, as we have determined. So you see, this has a maximum value. I could write here is largest when the angle between the vectors is equal to 0, because then cosine of phi is equal to 1. And this means that max, I could write it in this way, max of this one is equal to square root 2. So this is the answer. So this completes the second. Let me just take the last question. In the last question in problem 1, there's a curve given by this parametric representation. And we need to determine the points in K where the gradient of f and the tangent vector to this curve here are orthogonal. So let's try to do this. Let me see here. I have question 3. I have this parametric representation, and then 1 plus u minus u squared. And u is just any real number. So this is my parametric representation, and then I can determine the tangent vector to this curve here by differentiating with respect to u, and then you get 1 for the first coordinate, and for the second coordinate you get 1 minus 2u. Now you need to take the value, let me write it in this way, you need to take the value of the gradient of the restriction of this to this parametric representation. So remember, it was y divided by the exponential of x, so y is 1 plus u minus u squared divided by eu, ex, x is u. So this was the first coordinate. The second coordinate is 1 divided by eu. So in order for this vector, the tangent vector here, to be orthogonal to the gradient, their dot product must be 0. So let me compute times the gradient of f, this is r of u, and you get 1 times the first coordinate here, that is 1 plus u minus u squared. And then you get 1 minus 2u divided e to u. So this is the result. And if I made a mistake here, because you see, when you have the gradient of the function, it is minus y divided by ex. So I should have here, there should be a minus sign in front of this. And this means you have a minus sign here. And when you then put it on a common denominator, you get minus 1 plus 1, that is 0. You get u minus 2u, or you get minus u minus 2u, that is minus 3u. And then you get minus minus u squared, that is plus u squared. And this should be equal to 0 in order for the two vectors to be orthogonal. This you can solve. This is different from 0. You can get rid of this by multiplying by on both sides. And then you get that u is 0 or u is equal to 3. For these two values of u, the two vectors will be orthogonal. So what you just have to do then is to put in these values in your parametric representation, which I have here. It will be 0, 1, 0, 1. And then you have in this, for the u equal to 3, you get 3 divided by 4 minus 9, that is minus 5. So this will be 4 minus 5. So this is the result of the question. This completes the first problem in the exam exercise from last year. So let's see. I think I'll turn on a new canvas here, because then we will take problem 2 here. So let me look at problem 2. In problem 2, you are given a matrix, this one, and it has the eigenvalues 1 and 3, so you know this. And also each of these eigenvalues have eigenvectors. And you have a quadratic polynomial, and it's given like this. You see, it's a quadratic, and it includes a quadratic form. And let me just take this part of it. This is the quadratic form of the polynomial. And we should state a positive orthogonal change of base matrix Q that reduces the quadratic form such that in the new x1, y1 coordinates does not contain mixed terms. This is the usual problem of diagonalization of a matrix. So let's try to do that. So I'll return to my canvas here. So let me write the matrix. This is 2 minus 1 minus 1, 2. And you have the eigenspaces. You have the eigenvalue 1 and the corresponding eigenspace. It's the span of the vector 1, 1. And E2 is the span of the vector minus 1, 1. Now, if you look at your polynomial, your quadratic polynomial, then it's 2x squared minus 2xy plus 2y squared minus 4x plus 2y, and then plus 2. And you can write this as x comma or xy, this is the vector, and then times 2 minus 1 minus 1, 2, and then x, y, plus minus 4, 2, plus 2. And you see here you have your quadratic form. Quadratic form. I deal with your chat after this exercise here. Maybe I had made an error. Okay, but this is a quadratic form, and you see this is a symmetric matrix. And then you know that the eigenvectors corresponding to different eigenvalues, and you have, it should be 3, that should be the eigenvalue. Okay, so you have that these two vectors are orthogonal. So the only thing you need in order to have this orthogonal matrix is that you need to normalize these vectors here. And you do that by dividing by the length of the vectors, and the length of both these vectors is a square root of 2. So you can, in fact, immediately write down this orthogonal matrix. It will be square root 2 halves, square root 2 halves. This is the normalized first eigenvector, and then minus square root 2 halves and square root 2 halves. This is the second. So this is your orthogonal matrix, and then you know that the transpose Q times A times Q is equal to a diagonal matrix containing the eigenvalues 1 and 3 in the diagonal, 0 elsewhere. So this you know. Now you have diagonalized the system, and you know that because you knew the eigenvalues and the eigenvectors for the system. But now you can use this in order to get rid of the mixed terms in your quadratic form. And you do this by introducing new coordinates. So you use Q as a change of base matrix, where this is the relation between the new coordinates x1, y1, and x and y, where Q is given above. Okay. What we need now is that we need to compute, in order to have this vector here, we need this row vector x, y, and this is x, y transposed. Now xy is given as q times x1, y1, and you need to transpose this. And you transpose a matrix vector product by transposing each of the term and then interchange the order of the terms, so you get x1, y1 transpose times q transpose. And this is equal to, the transpose of this one is x1, y1, and then times q transpose. Now you can use this in the formula for the quadratic form. You have it here, and so you write that it will be x1, y1, and then times q transpose, and then you have your A matrix, and then you have your x comma y, and this will be q times x1, y1. And remember, this one here, this matrix here, is equal to gamma, or lambda, the lambda matrix. So you get that it will be x1, y1, and then you have 1, 0, 0, 3, and then you have x1, y1. So this will be x1 squared plus 3 y1 squared. So this is the result. Here we have gotten rid of these mixed terms. Let's try to look at the next question here, because now we have solved question 1, and in question 2 we have to, in this new basis, we have to write the quadratic polynomial in this form. So we have rewritten the quadratic form, this is this one here, of this quadratic polynomial, but we still have some terms, and then we should prove that it could be written in this way. Finally, when we've done so, we should explain that f has a local minimum in the point x0, y0 that corresponds to the point c, d in the xy, yy, or y1, x1, y1 coordinate system. Okay. Let's take question 2. So if I use this transformation, and if I go back, I can see I have rewritten this in new coordinates. I need to rewrite this part in u coordinates, and then or this part here, and then I have this constant. So this is done. I need this one, and I need this one. So let me do this. So I get, for the quadratic part, I just write f(x, y), and then or x1, y1. I have rewritten the first part. It is x1 squared plus 3y1 squared. And then I need plus, and then I have minus 4, 2, and then times my change of base matrix, and then x1, y1, and then plus 2. So let's see what this amounts to. So I need to multiply minus 4, 2 on my change of base matrix. Remember that was square root of 2 times, for the first column here, it was square root of 2 half, comma square root of 2 half. So that will be minus 4 plus 2. So this will be minus 4 plus 2, that is minus 2, so that this will be minus square root of 2 times x1, this was the first one, and then it will be, you have the second column, you have minus square root of 2, I write q again here, that is square root 2 halves, square root 2 halves, and then minus square root 2 halves, square root 2 halves. So when I multiply minus 4, 2, on the second column here, I get minus 4 times minus square root 2 halves, that is minus, that is plus 2, and then plus 1, so you get plus 3 square root of 2 times y1, and then plus 2. And now you need to complete the squares. So you have x1, and then you have minus square root 2. So this will give you minus square root of 2 halves. And if you multiply this out, you have added, say, the square of this, so you have to subtract this again. So that will be minus square root of 2, like this. Then you do the same thing in the y direction. You get y1. Now you have a plus. You put 3 outside the parentheses. So you have square root of 2 halves squared. And then again, you have to subtract the square of this. So this will be 3 times 1 half, and then plus 2. So you see you have minus 1 half, minus 3 halves, and plus 2, that is 0. So the result is x1 minus square root of 2, and then the square of this, and then you get 3 times y1 plus square root of 2 halves squared. And if you compare to the formula that was given in the text, you have that a is equal to 1, b is equal to 3, this one, and then you have that c is equal to square root of 2 halves, and d is equal to minus square root of 2 halves. So this was the answer to that part of the question. Let us just look at the second part. Now we have determined A, B, C, and D. And now we have to find the number x0, y0 that corresponds in xy coordinates to the point CD in x1, y1 coordinates. Let's try to do that. So you have, if I should find the xy coordinates, remember this was this change of base matrix, x1, y1. So, and if I take q, and then I have square root of 2 minus square root of 2 halves. And remember, you have square root of 2 half in the first row here, and minus square root of 2 half. So you get 1 half plus 1 half, and then you get 1 half minus 1 half. So that is 1, 0. Now, if you look at it, you have that f of 1, 0. If you compute this, this is equal to f1 of square root half, minus square root half, and you know this is 0. But moreover, you know that f of x, y minus f of 1, 0 is equal to f1 taken of x1, y1, and you know this is greater than 0 when x1 or x, y, I should say, is different from 1, 0. And you can look at it here. You see, you have two quadratic terms here, and they are different from 0 unless both these terms are equal to 0. So this means that f has a proper local minimum n 1, 0. This was problem 2. Okay, and I can see that there are R3 is 3, minus 5. Let me just return to use this one. Well, you are ever so right. So I'll just correct this one and write 3. Okay. So let me so we finished this one. Okay, I'll start a new note here for then I'll just use this one here. Let's look at the next problem. Well, in the next problem, we are given a surface And you can see that, well, this is a plot of the surface, but there's given, see here, a parametric representation of this surface. And in the first question, we should explain that this is a surface of revolution, and we should draw its profile curve in the xz plane, which is used in the rotation. So let's do this. We have here, I write here, problem 3. And we're given a real number greater than 0. And then we have this surface given by its parametric representation, which is u cubed times cosine v, and then u cubed sine of v, and then u. U is in the interval from 1/2 to 1, and v is in the interval from 0 to a. Let me just try to get rid of this. 0 to a. Okay. And in question 1, we should prove that this is a surface of revolution. So I write this in the standard form for a surface of revolution, where I use g of u times cosine v, then g of u times sine v, and then h of u. You see, I can write this form here write it in this general form, provided that g of u is u cubed and h of u is equal to u. And again, u is running from 1/2 to 1, and v is from 0 to a. Okay, and this you can look up in the eNotes. If you look up in eNote 25, page 11, then you can find that f is a surface of revolution of the curve u cubed, 0, u in the xz plane. Let me try to make a sketch of this. If we have, say here, this is the xz plane, and then you have that this is a cubic curve of the variable z. You see z is equal to u, and then x is u cubed. So it'll be a curve that looks, if this is 1 here, then it will look something like this. This is the general cubic curve here. But you see that Z is running from 1/2. Let me take another color here. It's running from 1/2 until 1. That is this part here. So it is this part of the curve here that is rotated around the z-axis in order to give this surface of revolution. Okay, let us look at the next problem here. We should simply determine the Jacobi function corresponding to R. Let's do this. We have, this was question 1. Now we go to question 2. I just return to white. Okay, this one. And then question 2. Remember, for a surface, the Jacobian is the length of the cross product of the derivative with respect to u of your parametric representation. Let's go back and see how you have this parametric representation here. And you want to differentiate this with respect to u. You get 3u squared cosine v, 3u squared sine v, and then 1. And for the derivative with respect to v, you get minus u cubed sine of v, that is the derivative of cosine of v, and then u cubed times cosine of v times 0. And if you then compute this cross product, you get, well, you have that it will be the second part of the first times the third part of the second minus the first part, and then so the first coordinate will be minus u cubed cosine v, and the second part will be minus u cubed sine of v, and then finally the last part will be 3u to the 5th power, and then times cosine squared of v plus sine squared of v, like this. This is simply this cross product. And remember then that the Jacobi function is equal to the length of this, that is cross RV. And then you simply square the first one, second one, that is u to the 6th power cosine squared v plus u to the 6th power times sine squared of v. And then finally you get 9 plus 9u to the 10th power, that is the square of this one. This one is equal to 1. So this is simply the result of this. And again, you can use a fundamental relation for trigonometric functions. So this will be equal to the square root of u to the 6th power plus 9u to the 10th power of u. And if you put u to the 6th power outside the square root sign, you get u, and then 1 plus 9u to the 4th power. So this is your Jacobi function. Now, let's just look at the last question here. Now we consider a mass density function, and it has the same value of the Jacobi function corresponding to R. And we should find the value of A. Remember, we have an undetermined parameter in our parameter representation, so that F attains the mass 1. And the function you're going to integrate then is the Jacobi function, but you have the Jacobi function when you evaluate this surface integral, you should use the Jacobi function, so you get the Jacobi function squared. Let's look at that. So question 3, you have, say, you have this mass density as, this is the Jacobi, and this means that the total mass will then be the integral from 0 to a. Remember that v is between these values, and u is between 1/2 and 1. And this will then be the Jacobi. This is your f value, and then you should multiply by the Jacobi. And then du dv. Okay. So you will simply have that you should integrate the square of this function. So this will be the integral from 0 to a and from 1/2 to 1 of u to the 6th power times 1 plus 9 u to the 4th power, and du dv. Well, you could do that. It's fairly simple integrals, but if you do it exactly, then you get some very long terms. You can do it in Mabel, of course, and the result will be that you see the integrand doesn't depend on v, so this the integral from 0 to a with respect to v is just a, and this integral of u between these bounds here is 15, 13, 13 divided by 15, 76, 96. And this should be equal to 1. Simple equation you can solve with respect to a, so you get 1576 divided by 15, 13. And this is approximately 1.04. So this is the result of this computation. And this completes the third problem in this exam set. Now, I think we should just go on to the next one. I'll just take a fresh note for this one. Yes, and let's look at the last. Okay, this is problem 4. And you see we have a triangle. We have a triangle with these vertices. And we should state a parametric representation for T, for this triangle. So let's just start by solving this problem. So I write here problem 4. Let me just depict this triangle, because you have, it's between 0, 0, and then let this, let me just work this out and I draw it a bit longer. So we can use this one, and then this is 2. So it is this triangle here, and we need a parametric representation. I could just say that this is 1, 0, and this is 1, 2. So these are the 3 points defining the triangle in the XY plane. I think I will use U as a parameter, U here. And when I have U, I have this vertical line, and let me just take the full line here. This line has the equation y equal to 2x. So when x is equal to u, then this point here is 2u. So then it's fairly easy to write down this parametric representation. I get the initial point, which is u, 0, and then another parameter. And this is, I take the final point, and this is 2u. Oh, sorry. I take, this is u, 2u. This is the final point, minus the initial point. So u minus u, that is 0, so you get u here. And down here you get 2u. And remember, u is between 0 and 1, and v is between 0 and 1. So this is your parametric representation of this triangle. So let's look at the, then we have a solid that is given in this form. It's shown here, and it's the solid lies above T, and it's limited vertically by the plane z equal to 1. And we should state a parametric representation for this solid here, and we should determine the Jacobi function for this parametric representation. Okay, let's try to do this. Question 2. So let me just show you x, y, or x. I have y here and z here. So I have my triangle. This is my triangle T. And then I'm limited by z equal to 1 in this way. So this is, so you see, I can still use as the first 2 coordinates of my parameter or parametric representation for this area here, I can use the parametric representation. Now I have a third parameter to describe this solid. I have, for the first 2 coordinates, I can use the same. I have u, I have 2 u. And in the third direction, I simply use the z coordinate. Call this v. And then you have that all the parameters u, v, w, they belong to the unit interval here, 0 to 1. So this is my representation. And then remember, when you should calculate the Jacobi function here, then the Jacobi, it's equal to the numerical value of the determinant that I write here, r prime v, and then r prime w. So the numerical value, so I have to differentiate this with respect to u. For the first column, I get 1, 2v, 0. And then for the second, I should differentiate with respect to v. I get 0, 2u, 0. And then finally, I differentiate with respect to w. I get 0, 0, 1. Now this is easy to calculate because it's a lower triangular matrix, so the determinant is the product of the elements in the diagonal, so it'll be the numerical value of 2u, but since u is between 0 and 1, this is equal to 2u. So this is a Jacobi function. And this completes question 2. Let's look at question 3. Now we are given a function f, and it's given by this formula here. And we are considering a vector field, or v, x, y, z, that is equal to the gradient of z. And given that vector field here, we should determine the flux of the vector field outside the boundary of this solid field. Let's try to do that. That will be question 3. So we have this function here, x squared, y, z, and this, and then we have a vector field, which is the gradient of f, and this will be 2x, y, z, x squared, z, and then x squared y. This is simply the first one is the derivative with respect to x, with respect to y, and with respect to z. Now I could write for each of these parts of the surface, I could simply write down the flux through the surface and then add all 6 surfaces together, or 5 surfaces, I guess it is. 1, 2, 3, 4, 5. 5 surfaces together, but I don't really feel like that. I will what I will do is that I will use the Gaussian theorem, or the Gaussian theorem, the divergence theorem. So I calculate the divergence of this, this field here, the divergence of V. So I should differentiate the first one with respect to x, I get 2yz, and then plus the derivative of the second one with respect to y, but it doesn't depend on y, so it's 0. And similarly, the third one doesn't depend on z, so it's also 0. So the divergence is 2yz. Now, the flux is then this derivative along the boundary of this dot product, like this. But due to Gauss theorem, it is also equal to the volume integral of the divergence of the vector field. And now we can simply write down this, because we know that we need to integrate from 0 to 1 in all directions. And then we need 2 times y, and the y is or it should be y in is, let me see, we have here, it is 2vu, I have it here in the parametric representation. It is 2vu. And then this was y, and then I have to multiply by z. But z is just w. And then I have to multiply by the Jacobi function, and the Jacobi function was 2u. And I integrate this with respect to du, v, and dw. And if you do this, it's fairly simple integrals. I won't take much more of your time, but 2 times 2 times 2, that is 8. And then you can see that u is to the second power, so this will give you 1/3. And v and w is to the first power, so that will give you 1/2. So this is the total result for the flux. Okay, let's take the last example, or the last question. A curve K that runs along 3 edges of sigma from the origin to the point P to 1 is shown in red on the figure. So I just take away this one. Shouldn't be there. But you can see here, you have this red line here that will take you from the origin O to the point P. And then you should, along this curve here, determine the tangential curve interval here. But let's do that. We have Q4, and we know that since V is a gradient field, then we have that this tangential interval is equal to the value of the function in the final point, and that is 1, 2, 1, minus the value at the initial point, which is the origin, 0, 0, 0. So this is simply, if you put this into the formula for f, you get 2 minus 0, it's equal to 2. So this is the final result of this exercise. I'll just okay. I'm just studying your. I'm just studying your chat. It's 90 to the power of 4. Okay, I'll just go through the afterwards and see if there are any errors. But this completes the thing here, and I think that Mads has answered the question about why it's the Jacobi square in that part of the. So this was the first time I tried this. So please write to me and see if this is something that you can use. And good luck with all the exercises this afternoon. You will be quite busy. If well, and Sarah will be with you in a while. And remember, there's a weekly test that starts at 6 o'clock. So I'll end this session now. And I thank you for being with me. Okay, bye-bye.